All right. Let's see, this is your week for asynchronous work. We're going to finish up what we're going to be covering from chapter 3, which means today we're finishing up 3.4, which we started already in class. So just kind of wanted to review with you what we talked about already, which should be in your notes. I started by giving you some algebra properties that we use for logarithms. One of them was the power rule for logarithms, which is if you're taking the natural log of a and a is being taken to the exponent of p, then you can bring that exponent out front and rewrite that as p natural log a. And this has nothing to do with the derivative. This is just rewriting the natural log expression. And it works for any log, whether it's base e or any base, any real numbered base. We have a similar rules for multiplication and division inside a logarithm. So if you're taking the log of a product, you can rewrite that as the sum of two natural logs. And if you're taking the log of a quotient, you can rewrite that as the difference of two natural logs. I also gave you some what not to do's. If we have the natural log of a, the whole quantity being taken to the p power, then you cannot rewrite that as p times natural log a. You can't just bring the exponent down in that case. It must be the case that the exponent's only being applied to that value a, not the whole logarithm. I also didn't want you to do this, which is a very common error. You cannot break up the natural log of a sum or difference into the sum or difference of two natural logs. Can't do that. Don't do that. Then I give you some rules for derivatives for log functions. First, a log base a, which we're going to get to in a little bit, and then a log base a for some function of x. So I gave you these two. Then recall from 3.1, we had some derivatives for bases other than e. So I reminded you of this formula. And then we talked about this formula, which we used a couple times for the natural log of x. If you're taking the derivative of ln x, their derivative is 1 over x. But we can also apply a similar rule to natural log of some function of x. We just have to chain on the derivative of the inside function. So we did that. And then I gave you a couple of examples using this. So we talked about how we could break up the log of a product into the sum of two logs, or we could alternatively just use the inside as u of x. And the cases that we discussed didn't really make much difference either way. Depending on the problem, you might find that it makes a big difference. We did that also for B. And then for C, we didn't have that option because for C, we had a difference inside of the logarithm. So we can't rewrite that in any way that would be useful to us there. Okay, so we did that last time. So I'm going to give you some more examples of taking derivatives with these logarithms. Let me see, I'm going to have to zoom, fix my focus here. Try to do that, see how it looks. Just keeps coming in and out of focus. All right, so D, we're going to look at h of x. And anytime I use h of x, that should tip you off that you're going to probably need the product rule. I just use that because then when I label everything with f and g, it doesn't get confusing. So this one is h of x equals x squared times the natural log of x. So in this case, we have a product of two functions. One of them is a monomial, and the other is the natural log of x. In order to take the derivative, we can let the first factor be f and the second factor be g. And then f prime is 2x and g prime is 1 over x. So this goes with that rule that I gave you earlier for the derivative of the natural log of x. Now to find h prime, you're going to use the product rule, same way that we have been doing since chapter 2. We're going to take f prime times g plus f times g prime. Now when you take the derivative of the natural log of x, because of the form of that derivative, sometimes you're going to have to simplify. So we are definitely going to have to simplify this one, but there isn't a whole lot to do. Just simplify between the x squared and the x, and you'll get 2x natural log x plus x, and there's your derivative. So nothing too crazy there. Now, the next one I'm going to give you kind of follows along with that don't do this rule that I gave you at the beginning. This is the natural log of x quantity to the fourth power. So I want you to really see the difference between this, which is not the same as the natural log of x to the fourth. So these two are very different quantities. In this case, only the x is being taken to the fourth power. But in our case, we're taking the entire natural log to the fourth power. So we don't actually have a case where we can use the power rule for logarithms here. But we can use the chain rule with the general power rule. So to take the derivative, we're going to treat this just like it was x to the fourth, and then we'll chain on the derivative of the inside function. So using that power rule, we're going to bring the 4 out front. It's not the power rule for logarithms. It's not that. It's for derivatives. We're going to rewrite the inside function, decrease the power by 1, and multiply by the derivative of the inside function. Now, this is fine. There's really not a ton you can do. I'd probably simplify this a little bit more by writing it as one fraction, just by putting that x into the denominator. Instead of multiplying by 1 over x, just divide by x. That's up to you. Just remember that you must have these parentheses around your natural log. Okay. So there's that. F. So this one is f of x equals the natural log of the sine of x squared. Now, notice the way that I said that. I didn't say it as sine squared x. I said the sine of x squared. That's probably the way you want to think about it when you take the derivative. So if I were you, I would rewrite this as the natural log. And anytime you're taking a derivative and you see this notation where you have the square between the trig function and the argument, I'd rewrite this as sine x quantity squared. They mean the same thing, but this is going to be easier for seeing the derivative. Okay, now I want to take you back to that rule that we had for taking the derivative of the natural log of some function u of x. The derivative with respect to x of the natural log of some function u of x is u prime over u. We're going to use that here, for example, f. In our case, we're taking natural log u of x, and u of x in our case will be the sine of x quantity squared. So we're taking the natural log of that whole quantity u of x. We've written that out. Now, I know that the derivative of my natural log is just going to be u prime over u. So this is going to be the denominator. In order to get the numerator, I just need to take u prime. To find u prime, I'm going to use the chain rule, which is going to use that general power rule, again, that we used in the previous exercise. So I'm going to bring the 2 out front, keep the inside function the way it is, decrease the power by 1, and multiply by the derivative of the inside function. Okay, so now we can write our derivative f prime. Remember, we're going to take u prime, and we're going to divide it by u. So we're going to take 2 sine x cosine x, and we're going to divide that by sine x squared. If you want to write that like this, just because you're squaring it, you're multiplying it out, if you find that easier to do, that's fine. Go ahead. That makes it easier to simplify. So you'll have 2 cosine x over sine x. And you can rewrite that as twice the cotangent of x. You know, it's interesting. I'm looking at my notes, and I actually did it a little bit differently when I did this the first time. And maybe the way that I did it the first time was easier. And, you know, I said I don't really love doing alternate solution processes for calc students. But if you're wondering, like, could we have used that power rule for logarithms? You actually could have done that in this case. And your work would have been a little bit lighter if you recognized that you could have used it. And you probably would have recognized that right here. So you're taking the natural log of some quantity to a power. That means that you can rewrite f of x as twice the natural log of sine x, because the square is being applied to the argument inside the natural log. And then to get f prime, you're taking twice, so there's your constant multiple, and then the derivative of the inside function divided by the original, so u prime over u. Now in this case, u of x would be sine x, and u prime would be cosine x. So we'll have twice sine x, oh, sorry, u prime over u, I got that backwards, cosine x over sine x equals twice the cotangent of x. So notice how by rewriting this using that power rule for logarithms, we actually arrived at the same conclusion a little bit faster in that case. So just to illustrate the way that works, let's do some more of these, because why not? I feel like the more examples you see, the better you will be. All right, this is f of x equals the natural log of, all right, now get ready for it, the natural log of x quantity cubed. Okay. So the natural log of x cubed. So you can let this inside function be your u of x. So you're taking the natural log of some function u of x. So u of x is the natural log of x cubed. And then u prime is going to be 3 times the natural log of x squared, and then use the chain rule to chain on the derivative of the inside function. So u of x actually looks very similar to what we did, if you'll recall. For example, e, you had the natural log of x to the 4th power. Same idea here, it's just that we are using natural log of x to the 3rd power. So you take the derivative, using the power rule, chain on the derivative of the inside function. And then you can use that rule where f prime of x is u prime over u. So 3 times the natural log of x squared times 1 over x divided by the natural log of x cubed. And then you'll simplify. So you can cancel out 2 factors of the natural log of x. So both of the ones in the numerator will be gone. And then that leaves you with 3 in the numerator. And then this x in the denominator of the numerator is going to pop down into your denominator. And then we just have natural log x to the 1st power left over. So that's how we would simplify that one. And you could also try this one using the power rule for logarithms. Let's see, we'll do h. This is y equals the log base 2 of x. Now, way back when I gave you a formula for the derivative of the log base a of x, I'll remind you what it is right now. The derivative with respect to x of log base a of x is 1 over x natural log a. So we're going to use that rule here. So we're going to take 1 over x natural log a. Now remember, a is the base. And that's it. You're done with that one. There's nothing more to do. We use the rule, stick a fork in it, it's done. I'm going to keep this handy because next we're going to do another one of those logarithms with a base other than e. And this time we're going to have some function of x. So that will look like y equals the log base 8 of x plus 3 to the x. And now, if you're wondering, why did she even bother giving us that formula from 3-1 over again at the beginning of this? It didn't make any sense. Well, you're going to see now that you're going to use it for this problem. Because when you take the derivative of the inside function, you're going to have to take the derivative of 3 to the x. So my recall, I'm going to remind you of here, I'm going to even rewrite it here again. I gave this to you at the beginning of 3.4. I'm just going to write it down here one more time because we're going to refer back to it. A to the u of x, a to the u of x, ln a du dx. Okay, so we're going to use that. And we're also going to use this formula that I gave you for finding the derivative of log base a of u of x, because that is what we have here. Kind of rearrange this a little bit so we can refer back to it. Oh, maybe not. I can never figure out exactly how to place these in my particular Zoom. Okay, well, I'll just remind you of what the formula is, and then we'll use it. You're probably looking at it right now in your notes anyway. So the derivative with respect to x of the log base a of u of x is u prime of x divided by u of x times the natural log of a. So this I gave you at the beginning of 3.4. Okay, so these formulas we're going to use together to find the derivative of this example I. Okay, so we have log base a of u of x. So we're going to let a, of course, be 8 because that's your base. And u of x is going to be x plus 3 to the x power. So in order to find my derivative, I also need to find u prime. So u prime of x is going to be, well, the derivative of x is 1, and then the derivative of 3 to the x is going to follow along with this form. The derivative of a to the u of x, well, we don't really have u of x in this case, we just have x, but that's okay. Is going to be a to the u of x, so that's 3 to the x, times the natural log of a, well, a in this case is 3, times du dx. Now, in our case, du dx is just 1 because we just have x in the exponent. So we don't have to worry about taking the derivative of u with respect to x, because when we take that derivative, we just get 1. I mean, you can write it down if you want to, but it's unnecessary. Okay, so now we're going to use this formula to find the derivative of log base 8 of x plus 3 to the x. So y prime is going to be equal to, so we're taking u prime of x, which is 1 plus 3 to the x ln 3 divided by u of x, which is x plus 3 to the x. And I put that in parentheses because that's going to get multiplied by the natural log of a, which is the natural log of 3. Oh, no, sorry. A in our case is 8. Totally forgot that we have actually 2 different a's going on here. over here to find the derivative of u, a was 3 because the base is 3. But when we use this formula to find the derivative of log base a, in this case, we're using 8. So when we did u prime over u, we used u prime and u. And then when we divided by the natural log of a, we're dividing by the natural log of 8. Now, I want you to be careful here not to cancel out anything like the 3 to the x's. You can't do that because you don't have a 3 to the x in every single term. And like I said, remember your parentheses. That will make a very big difference. Don't put parentheses around the 1 plus 3 to the x because that's not what you mean to say. Your u prime actually doesn't take 1 and multiply it by ln3. So you don't want to put parentheses there. So 1 plus 3 to the x times ln3. I want to make sure everyone understands the use of parentheses. Okay, so that was I. We'll use this rule again in J with the product rule. Everyone is just ruining the day they learned the product rule. So this is the natural log of x times 4 to the x power. I'm going to write this down for you again, just because now it's far away. I gave you on the previous page the u of x variation of this, but since we only need the x, let's just use this variation. Okay. All right, so we're taking the natural log of a product. Remember that, oh, actually, we can avoid the product rule by rewriting this natural log as the sum of two logarithms because we have the natural log of a product. So we're going to use that logarithm rule that allows us to split this up into the natural log of x plus the natural log of 4 to the x. Now, the derivative of natural log x is just going to be 1 over x. But the derivative of natural log 4 to the x, for some reason, this is bothering me without parentheses. Maybe because I really wanted to do this and call it u of x. So I'm not worried about the first one, like I said. The derivative of natural log x is 1 over x. This one, we're going to just take u prime over u. No big deal. So if u is 4 to the x, then we would say that u prime of x, using this formula, is 4 to the x times the natural log of 4. So u prime over u is 4 to the x ln 4 divided by 4 to the x. And then those 4 to the x's are going to cancel out. And you'll just be left with 1 over x plus ln 4. Okay, so we've used those rules a couple of times now. We're going to let them go for a while until you see them on your homework. Okay, so this is f of x is the inverse sine of the natural log of x. So now we talked about derivatives for inverse trig functions in 3.3, and I gave you a rule for finding the derivative of the inverse sine function. It was u prime divided by the square root of 1 minus u squared. So let's go ahead and take this derivative using u of x equals ln x, and then u prime of x is 1 over x. So the inverse sine of this function, the inverse sine of the natural log of x, is going to be u prime divided by the square root of 1 minus u squared. And I don't know, like there's not like a whole ton you can do here. I would just pop this x into the denominator and write it like this. I have seen some students and teachers randomly, and this is fine, I just want to show it to you. Instead of writing like the natural log quantity squared, they write it kind of like how we would write, like a sine squared x. If you want to use this notation, that's fine. Be my guest. Go ahead. It doesn't bother me. And if you've never seen it before and you like this one better, that's fine too. But this is just taking the inverse sine of u of x and just applying that inverse sine formula that you learned at the beginning of 3.3. Okay, now this one is going to look similar, but it's not the same. This one is f of x equals the natural log of the inverse sine of x. Okay, so again, the derivative of the natural log is u prime over u. In our case, u of x is the inverse sine of x. And the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, because the derivative of x is 1. And now when we take f prime, the derivative for the natural log of u of x is u prime over u. So we're going to take 1 over the square root of 1 minus x squared and divide it by the inverse sine of x. Now, of course, this is a complex fraction. Instead of dividing by x, you can think about it as, or I'm sorry, instead of dividing by inverse sine x, think about it as multiplying by 1 over inverse sine x. And then what you're going to end up with here, and it kind of depends on how you want to write it, will be the inverse sine of x times the square root of 1 minus x squared. Okay, so remember that this is just u prime over u. And then we simplify it. If you like to put parentheses around this, if you feel like it looks like it's too bunched up, that's fine. You may do that. No big deal. All right, example 2. So we're done with just find the derivative involving logarithms. Now we're going to apply that to some other things that we've done with derivatives throughout the chapter. Find the equation for the tangent line. And we'll do, I think, 2 of these. Oh, actually, I have another one of these because I wanted to do a log that wasn't a natural log. Okay. All right, so A is y equals the natural log of the tangent of x. And we're going to let x be pi over 4. Now, sometimes you're going to be given right away the point. Usually in this book you are. Sometimes you're just given a value for x. So since we know we're going to find the equation for the tangent line and you know you're going to need c and f of c, you might want to just go ahead and, if you think about this as f of x, just find f of pi over 4. So if you do that, just to get the y coordinate for the point, you're looking for the natural log of 1, because remember the tangent of pi over 4 is 1. The natural log of 1 is 0. I also want you to get used to these natural log values. You can put this in your calculator if you haven't done that in a long time. I'll remind you of how to do that. Oh, maybe not. Let's see. Okay. So natural log is right here, ln, and it's going to open up a natural log for you with the parenthesis, and you're going to enter 1, and it's going to give you 0. But that's one that I expect you to just know. And most of the time, I don't want approximate values. Like I'm not going to ask you to approximate the natural log of 3 unless I specifically ask you to round it. I just want the exact value, which is ln 3. But if it has an exact integer value, then we'll use it. So this is actually the point pi over 4, 0. So we're going to use this when we write the equation for our tangent line. But first, we need to find the slope. And to find the slope, I need to go ahead and take the derivative and then evaluate the derivative at pi over 4. So the derivative is going to be u prime over u. Off to the side, if you want to write u of x is the tangent of x. That's your inside function. And then u prime, remember the derivative of the tangent of x is secant squared x. So when you take your derivative, y prime, you're taking u prime, which is secant squared x, divided by u, which is tangent x. Now you're looking for the slope at pi over 4 is 0. So go ahead and evaluate this at pi over 4. Remember, this vertical line basically just means like, give me a value. So we're looking for the secant of pi over 4 squared divided by the tangent of pi over 4. So we know the tangent of pi over 4 is 1. The secant of pi over 4 is really just 1 over the cosine of pi over 4. Now, I know we don't usually create these complex fractions, but first of all, the denominator is 1. Second of all, we know more about the cosine than we do the secant. So go ahead and use that. So 1 over, and then if you want to think about that as root 2 over 2, fine. If you want to think about it as 1 over root 2, you'll probably have a little bit of an easier time with the quantity. So that's the cosine of pi over 4 as 1 over root 2. And then we'll square this quantity. If you'd like, you can rewrite the fraction. Instead of dividing by 1 over root 2, you can multiply by root 2. And what you're really getting here is root 2 squared, and root 2 squared is 2. So this is your slope. Okay, now I'm going to take the slope with my point, which is pi over 4, 0, to write an equation for the tangent line. So y minus y sub 1 is m times x minus x sub 1. And you end up with y equals 2x minus, and then twice pi over 4 is pi over 2. So that's that one. All right, now let's work on one that has a logarithm with a base 10. This will be y equals, and I'm going to write this 2 ways. I'm going to give it to you both ways. Log 2x, and I want you to note that that's the same as log base 10 of 2x. So remember, when the base is not listed, it is assumed to be 10. We're going to look for the equation of the tangent line at the point 5,1. Just going to go ahead and give you the point here. So let's go ahead and take the derivative. I'm going to remind you of your derivative rule from page 1. So for a log base a of u of x, I'm going to just write it down, but it was this one. The derivative with respect to x of the log base a, that means anything other than e, of u of x, I mean, technically it also works for e, is u prime over u. And the difference here is that you just have to multiply in the denominator by the natural log of a. So d dx log base a of u of x is u prime of x divided by u of x ln a. I'm just rewriting that so it's closer. You can kind of see me refer back to it. So in our case, u of x is 2x. And then clearly u prime would be 2. And a would be 10, because this is a log base 10, and a is that base. I keep almost asking, like, does anyone have a question here? That would be creepy if someone logged on to our call right now. Thanks. Okay. So let's go ahead and find y prime. So y prime is u prime over u. So that's 2 over 2x times the natural log of 10. And then we'll go ahead and find our derivative, or I'm sorry, simplify our derivative. That's 1 over x ln 10, just by canceling out these 2's. Don't forget that you still have a 1 in the numerator. I saw a couple of people on the test cancel out the only term in the numerator, and then they said it was 0. Everything was wrong after that. Got to be careful. We're going to evaluate this at x equals 5, which means we're looking at 1 over 5 ln 10. And that is your slope at 5, 1. Sorry, I almost said 1, 5. So now we can go ahead and use the slope with our point 5, 1 to find the equation for the tangent line. So we have y minus y sub 1 equals m, which is the slope we just found, times x minus x sub 1. And then, we'll simplify this as far as we can. So we'll have x over 5 ln 10 minus, and now when we take 5 times 5 over, 5 over 5 ln 10, you can cancel the 5's, and that leaves you with just 1 over ln 10. And then just add 1 on both sides. You don't have to get too crazy about this. So minus 1 over ln 10 plus 1. And that's good enough for me. And it's definitely good enough for WebAssign from what I've seen lately. So this would be the equation of the tangent line. Remember, you can always go to Desmos and graph your original log function. I mean, this log function you could actually graph in your calculator. Honestly, some of this stuff is a little faster on Desmos, but you could even graph this tangent line and verify that it is tangent to the graph at 5, 1. Okay. So we're going through what we need to do here as far as what we've done in this chapter. So we just found equations for tangent lines. Now we're going to take implicit derivatives because we love that. Oh, we love it so much. Example 3, I'm just going to do one of these. You don't have very many on your homework that I can remember. Differentiate implicitly. Okay, so the expression is going to be 4xy plus the natural log of x squared y equals 7. Now, right off the bat, you should notice that this actually isn't as bad as you would have initially thought, because instead of having to take u of xy as x squared y, this is actually the logarithm of a product. And normally we'd have to use the product rule, but in this case, we can just split up the logarithm using properties of logs. So we can write this using the sum of two logs because we're taking the natural log of a product. So I can rewrite this as natural log x squared plus natural log y. Now I haven't actually taken a derivative yet. All I'm doing right now is just rewriting the expression so it helps me to have an easier time taking the derivative. You might also want to use that power rule for logarithms to pull this 2 out of the exponent and bring it in front of the logarithm. Now you're going to have a much easier time taking the derivative implicitly. Now, you're not going to be able to escape the product rule entirely because you still have this product here in your first term with f and g. But at least you won't have to worry about having a product inside your logarithm. So f prime will be 4, g prime will be dy dx. Okay, so again, I haven't actually taken any derivatives for these first 3 lines, but now I'm going to take the derivative implicitly. So starting with the first term, we're going to take f prime g plus f g prime. So f prime g plus f g prime. So there's the f prime g. Sometimes it helps people when I label this. And then f g prime. So that's for the first term. For the second term, the derivative of the natural log of x is 1 over x. So if you just want to write that as 2 over x, just by pulling that constant multiple in front or into the numerator, that's fine. The derivative of 1 over y then is going to be 1 over y dy dx. Don't forget your dy dx. It still applies even though we have a natural log because you're taking the derivative of y with respect to x. And then on the right-hand side, don't forget to take the derivative of the constant and set it equal to 0. Okay, now I'm going to get all the dy dx's, and I think I'm going to leave them on the left-hand side. So I have 4x dy dx plus 1 over y dy dx equals negative 4y minus 2 over x. So we change the side, change the sign. Factor out your dy dx. And then divide to solve for dy dx. So we'll have negative 4y minus 2 over x divided by 4x plus 1 over y. Now, officially, this is your derivative. However, it's not simplified. I'm going to rewrite the expression so that when we simplify the complex fraction, you can kind of see where everything is going. Again, I'm rewriting it just because you don't want to mangle up the original. Otherwise, you're going to look at it later and be like, what the heck, where did that come from? And you're not going to realize that you did work to it later. Your LCD is x times y, the product of your 2 unique denominators. So go ahead and multiply every term by x times y. I forgot to grab a separate colored pen. That's okay. Offset that. And you don't want it to look like subtraction, so you might want to use parentheses there. Okay, so it's always hard to cancel out x's because they have slashes in them. Okay, those are the y's. So in the first term of your numerator, I have negative 4x times y squared. I have 2 factors of y. And then minus 2y divided by 4x squared y plus x. And that is your dy dx. I did not ask you to find the equation of the tangent line here. We're going to do one more of these, and that's where you're going to find the equation of the tangent line. how are we doing? You guys doing all right? It's going to be A-OK. Example 4. Find the equation of the tangent line. And yes, I know we already did this, but we didn't do it with implicit differentiation yet. Your equation is x plus y plus 1 equals the natural log of x squared plus y squared. Now, the last time we had a natural log in an implicit problem, we had a product inside the natural log, and that worked out really nicely for us because we were able to split it up into the sum of two logarithms. We actually can't do that here. Remember, you cannot rewrite this as natural log x squared plus natural log y squared. There's no property that allows you to do that. So we're going to have to just go straight chain rule here. Let's go ahead and just kind of set this up. This is our function u in x and y. And we know that the derivative of the natural log of u of x normally is u prime over u. So we have u of xy being x squared plus y squared. And then u prime of x and y will be the derivative of each one of these terms. So 2x plus 2y. And don't forget, when you're taking a derivative, you must tag on your y variables dy dx. You didn't need to do that here because you didn't actually take a derivative here. Okay, so we have a plan for the right-hand side. For the left, we don't really have to worry too much about it. It's pretty basic. The derivative of x is 1. The derivative of y is dy dx. The derivative of 1 is 0. Don't worry about writing that. And the derivative of your natural log is going to be u prime over u. So 2x plus 2y dy dx divided by x squared plus y squared. Now, you have a couple of options here. I don't know which one's better. You could multiply both sides of the equation by x squared plus y squared. Honestly, I don't know if that would be easier or not. The other option I was thinking of was, because I don't want you to think there's only one thing, you could split up this fraction using an LCD of x squared plus y squared. That might be kind of messy. Yeah, let's go ahead and multiply through by your denominator. So I'm going to, again, rewrite my expression. So that your notes look nice. I'm only doing this for your notes. Okay, now we're going to multiply both sides by x squared plus y squared. Don't forget your parentheses. And then, boop, it's gone from the denominator of the right-hand side. Okay, now this might seem odd to you, but don't feel like you need to FOIL this whole thing out. If I were you, I would take x squared plus y squared as just one quantity and just distribute the quantity into your parentheses. That's what I'm going to do. I'm going to take this whole quantity x squared plus y squared and multiply it by 1, and then add that to x squared plus y squared times dy dx. I think that's just going to be the easiest way to go. So x squared plus y squared when I multiply by 1, and then plus, and now I'm going to have to use my parentheses because this quantity is getting multiplied by dy dx. I don't have to actually distribute that at this point. I can just carry the whole thing over, but it's important that we make sure our notation is correct. And there's your right-hand side. All right, I'm going to get all the dy dx's on one side. I'm going to just stick with the left-hand side. Whatever. I've already chosen the side. Just let it be. Minus 2y dy dx equals 2x minus x squared minus y squared. So change the side, change the sign. And then we'll factor out the dy dx, then we'll solve. So you'll have x squared plus y squared minus 2y. And you saw that we had a lot of options in this problem. So I just never want you to think that for these implicit derivatives, everyone's are going to look the same. There are just a lot of things that you could do differently that's going to make your derivative look a little bit differently, at least midway through. All right, we have 2x minus x squared minus y squared divided by x squared plus y squared minus 2y. Oh, I didn't give you a point? Sorry. Find the equation of the tangent line. We're going to look at this at the point 1, 0. Whoops. All right, so I gave you 1, 0. Let's go ahead and evaluate your derivative there so we can get the slope. Everywhere you see x, substitute 1. Everywhere you see y, substitute 0. So you'll have 2 minus 1 divided by 1 is 1. And there's your slope. Just try to put a box around it. And then we'll find the equation of the tangent line. Y minus y sub 1 is m times x minus x sub 1. So y equals x minus 1. Done. Okay. So we've talked so far here and there about how to rewrite a logarithm by expanding it so that you can sort of break it up into smaller pieces so the derivative's a little bit more straightforward. What we're going to do now is I'm going to give you an example where we're using properties of logarithms to expand out your function, and then we'll take the derivative and it'll be much simpler than it would have been otherwise. And then that's going to lead us into this idea of logarithmic differentiation. And I'm going to end on that. So we have 3 more examples if you're counting. Example 5. Use log properties to find y prime. So I'm going to give you a big honking logarithm, and we're going to break this down to make the derivative easier for us. And it's going to be a log of a fraction. And in the denominator, we have a 4th root of x squared plus 2. So in the numerator, we have x squared times the quantity 2x cubed minus 1 cubed. And then in the denominator, we have the 4th root of x squared plus 2. Now, when you're taking the log of a quotient and you're trying to break this down, because notice that, by the way, if we didn't use log properties to find the derivative, you'd be in a huge mess here. Not only would you need to, I mean, okay, so u of x would be this giant thing. Then you'd have to take u prime, which would be like chain rule, quotient rule, product rule all together. It'd be like a nightmare. I don't even want to do that. Even if I don't want to do it, you know it doesn't look pleasant. Okay, let's rewrite this. We can take the log of a quotient and rewrite it as the difference of 2 logs. So start out by doing that. The fraction is like that first thing that you should undo. So I'm going to take the natural log of x squared times 2x cubed minus 1 quantity cubed minus the natural log of the 4th root of x squared plus 2. So just splitting up the fraction using the difference of those 2 logarithms. And we have a bunch of things we can do here. I do want to end up using the power rule to sort of pull out these exponents. Right now, you might want to notice that you have the product of two functions, which you're going to need to split up before you can use the power rule for logarithms. So I'm going to take the log of this product, x squared times 2x cubed minus 1 cubed, and split it up into the sum of two logs. So you can take the natural log of x squared plus the natural log of 2x cubed minus 1 quantity cubed. And then if you want to rewrite the last one with a 1/4 power, since it's a fourth root, you will find that that's going to make your derivative a lot easier, and you're going to be able to pull that power down. And now really all I have to do is apply the power rule 1, 2, 3 times before I take the derivative. Now remember, I haven't actually taken a derivative yet. I'm just rewriting the function so that it's easier for me to take a derivative. Oh, look at this. I'm talking about derivatives, and then I went and wrote y prime. We're just still working on y. So bring those powers down. 2 ln x plus 3 ln 2x cubed minus 1 minus 1/4 ln x squared plus 2. Okay, now this is fully expanded. There's really nothing else we can do here to continue to expand this. Remember that I can't break up the difference of the difference inside a log. I can't break up the sum that's inside a log. That's just the way it is. That means I can't pull this 3 out front because I can't split those terms up. So this is done. We haven't taken the derivative yet. I just mean rewriting the expression is done, using properties of logs to rewrite y. Now we're going to take the derivative. Okay. So the derivative of ln x is 1 over x. You can write that as 2 over x. And then remember, we're taking u prime over u. So if you let u be 2x cubed minus 1, you can leave the 3 in the numerator. U prime is going to be 6x squared. So the 3 came from your constant multiple, and the 6x squared came from the derivative of u of x. All right, do the same thing with your last term. Take u prime over u. The derivative of x squared plus 2 is 2x. Divide that by x squared plus 2. And there's not a whole lot you can do here. Just do what you can. You can at least simplify between the 2 and the 4. 2 over 4 is also known as 1 over 2. And then maybe just rewrite this as 2 over x plus 18x squared divided by 2x cubed minus 1 minus x over, don't forget your parentheses to distribute, twice the quantity x squared plus 2. And there it is. That's good enough. Okay. I almost wasn't going to cover logarithmic differentiation, but then I remembered that it does appear in later chapters, and occasionally your Calc 2 teacher might use it. I know that I was using Dr. Campbell's Calc 2 shell last semester, and it did show up there. So I'm going to do the logarithmic differentiation. It's not crazy. It's just basically a play off of what you just did here using these properties of logarithms. So let's go ahead and figure out the logarithmic differentiation in example 6, and I'll give you 2 of these. Use logarithmic differentiation. Okay, and if you're just like, what the heck, I don't know what that is, well, I'm going to show you what it is. A. I'm going to give you a little bit more of a basic one to start out with. So this is x minus 1 to the x power. So logarithmic differentiation is used a lot of times when you have a derivative that would be a little more complicated. In this particular example, you have u of x to the x power. So the reason we might want to use logarithmic differentiation on something like this is because if we apply a log to it, we can use the power property to get the x out of the exponent. Right now, you only really have derivative rules for a to the x, where a is some real number, or a to the u of x. But you don't have a rule right now for u of x to the x. So you kind of would have to do this using logarithmic differentiation at this point. In order to do that, we're going to take ln on both sides to get the variable out of the exponent. I'm going to sort of write my steps here. So we're taking the natural log on both sides to get the variable out of the exponent. And you've done stuff like this before, just not with derivatives. Back in algebra, you at least worked with taking logarithms on both sides and pulling that exponent out when you were solving exponential equations. All right, so ln y is ln x minus 1 to the x power. So as long as you do it on both sides, then you haven't really changed your equation at all. Now you're going to use the power rule to bring that variable out front of the logarithm. Once you have that out front, now you're going to differentiate implicitly. So we're going to take the derivative on both sides. The derivative of ln y is going to be 1 over y dy dx. Now on the right-hand side, you're going to have to use the product rule because you're multiplying x times the natural log of u of x. Now, of course, f prime is 1. G prime is u prime over u. So when we take the derivative, we're going to take f prime g. So 1 times ln x minus 1. Sorry, I kind of bunched all this together here. So that was f prime g plus f times g prime. And we don't have any y's on the right side. So on the right side, we don't need to worry about taking any or including any dy dx's. Okay, now we're going to solve for dy dx. Before we do that, I'm just going to simplify this a little bit so it looks a little bit better. So this is going to be the natural log of x minus 1 plus x over x minus 1. Now, to get dy dx by itself, we're going to multiply both sides by y. To isolate dy dx. Multiply both sides by y to isolate dy dx. So remember, I want to get dy dx by itself because that's what I'm looking for here. And I'm going to take y. I'm going to multiply it by ln x minus 1 plus x over x minus 1. I'm putting the whole thing in parentheses just because I want to show that that quantity is being multiplied. And then you might be wondering, like, okay, but this says dy dx, everything's in terms of x and y. Well, here's the kicker. you have this y here. You're going to swap it back out. We're going to back substitute. So the y that you ended up dividing or multiplying by on both sides was originally x minus 1 to the x power. It still applies. So we're going to back substitute. Whoops. Back substitute. Y equals x minus 1 to the x power, because I want everything to be written in terms of x. And then I'll have the derivative of y with respect to x. So x minus 1 to the x. And then you can probably just leave that factored. Yeah, that's what I did. This is y prime. I mean, same thing. And these, a lot of times, are not going to look pretty when you're done with them. And I had a student last semester. She was so precise about everything, and she always wanted everything to be simplified just right. And these logarithmic differentiation questions drove her insane, because she got to the end and was just like, I can't leave my answer like this. I need to simplify. What do I do? And sometimes there's not a lot you can do. You just have to accept the fact that it's going to look kind of messy. And some of you will be thrilled with that, because you don't want to have to simplify your answers. You want it to look messy and you don't care. And that's fine. Lucky for you, you can do that with these. Okay, so we started out by realizing that we needed logarithmic differentiation because we don't have a differentiation rule for u of x to the x. So we took a natural log on both sides to get the variable out of the exponent. So natural log on both sides, use that power rule to pull the x out, and then we took the derivative implicitly. Once we had that, we were able to multiply both sides of the equation by y, and then we back substituted it for the original expression. Now we're going to do one more of these. Last one. And then you will be done with chapter 3, or at least you'll have your test and then you'll be done with chapter 3. You know what? I have this big, well, it's not really a crack in my table. It's really where the two ends meet in case I want to put the leaf in. It's probably going to drive me crazy because I'm on my last page, which was, as luck would have it, I pulled the exact number of pages out. But since I'm on the last one, it's thinner. I don't want to be running into that crack in my table. When my oldest son was like 2 years old, he used to stare into my eye and he would say, "You have a crack in your eye." I don't know what he was talking about. Maybe he was talking about my wrinkles. I don't know. I could never figure that out. So when I think of cracks in my table, think of the cracks in my eye that may or may not still be there. Okay, so this one now. Remember, the directions are still use logarithmic differentiation. So this is just part B of that. And if you're wondering, like, okay, well, this one's a little different than the last one. And the last one I had an x in the exponent and an x in the base. And this one I don't have that situation. Well, that's true. So the nice thing, though, about logarithmic differentiation is when you apply a log on both sides, the logarithm is going to allow you to take this crazy expression and simplify it down so the derivative's a lot easier. Because if you did not have logarithmic differentiation, you'd be looking at product rule, chain rule, quotient rule, all in the same problem. And nobody wants to do that. Not even me. I mean, I would if I had nothing else going on. But, you know, it's like 2 in the morning. And I already taught you guys earlier tonight. And then I did my 5-mile run. And I'm just real tired. So this is not something I'd be interested in doing right now if it wasn't for logarithmic differentiation. But we have it at our disposal, so I'm going to show you how to use it. Okay, remember, we're going to take the natural log on both sides. square root x cubed plus 2 squared divided by the cube root of 3x plus 4. Okay. Now, this is going to look very much like what we did, for example, I want to say 5, where we simplified, example 5, use log properties to find y prime. This is going to look very similar to that. It's just that we're including now this component where we have this implicit differentiation. Okay, so this wonderful, wonderful thing has occurred where now we can rewrite our expression. I'm not taking the derivative yet. All I'm going to do is rewrite this expression using the properties I have for logarithms. So let's go ahead and break this up. I'll break out the quotient. So the natural log of a quotient is just the difference of two natural logs. So we'll take the natural log of the numerator. First, we'll split it up that way, minus the natural log of the denominator. Okay. And this, like I said, is very similar to that example that we did, example 5. So you're going to also notice that before we can use that power rule, we have to actually split this up. I need to have the power only applying to one quantity. Or I'm sorry, it has to apply to any quantity in there. And right now, the square only applies to the x cubed plus 2, does not apply to the x. So I'm going to have to split this up, but that's okay because it's a product. And I can take the natural log of a product and split it up into the sum of two natural logs. So I'm going to write this as the natural log of the square root of x plus the natural log of x cubed plus 2 quantity squared minus the natural log. And because I know I'm going to want to get rid of this radical, I'm going to go ahead and write the cube root as the 1/3 power. And now the last thing I have left to do here is just to rewrite powers in front of the logarithms. And really, this is x to the 1/2. I feel like we should be able to make that leap pretty quickly. But the square root of x is x to the 1/2. So I'm going to pull out the 1/2 in front. And then I have twice the natural log of x cubed plus 2 minus 1/3 times the natural log of 3x plus 4. Now, again, I have not taken a derivative yet. I know it seems like we've been doing all this work. We have been doing all this work, but because we're preparing to take our derivative. And some of you might be like, wow, I could have already done the quotient rule, product rule, and chain rule at this point. I don't think so. You could have tried it, but it would have been very confusing, and you might not have been done with it. So this is better because this is just algebra at this point. And the derivative is going to be much more straightforward. All right, are we ready? We're ready. I'm ready. Okay, natural log x. Let's go ahead and take the derivative. Gosh, here we go again. I was not ready. I just kept rewriting. Let's take the derivative implicitly. When we do that, we'll get 1 over y dy dx. Gosh, this is like the most talking I've done in a long time. It's very sad. Okay, 1 over y dy dx is 1/2 times 1 over x. So the derivative of the natural log of x is 1 over x. And then we'll do u prime over u. So the derivative of x cubed plus 2 is 3x squared. And then we'll divide that by x cubed plus 2. And this 2 is just from the constant multiple. So whether you want it in front of the fraction or in the numerator, it doesn't matter, you pick. And then we have minus 1/3 times, and then again, we'll do u prime over u. So the derivative of 3x plus 4 is 3, and then divide that by 3x plus 4. And then simplify. So the 3's clearly are going to go. So I have 1 over 2x plus 6x squared divided by x cubed plus 2 minus 1 over 3x plus 4. Okay, So once you've simplified the right-hand side, remember we're trying to find dy dx. So we're going to multiply both sides by y, just like we did last time. So we're going to say no big deal, dy dx is y times this whole quantity. And now you can start to see where this is going, where you're going to end up with a really crazy expression. And know that I'm expecting that. I don't expect you to have a really super simplified expression here. It's just not going to happen. All right, I want my answer only in terms of x, so I'm going to back substitute. And I'm not even going to write what y is equal to. I'm just going to refer back to it here. It's in the problem statement. Y is the square root of x times x cubed plus 2 quantity squared divided by the cube root of 3x plus 4. I'm going to sub that back in. And hopefully you're looking right at it on your page because I don't have enough room to include that. So we have the square root of x times x cubed plus 2 quantity squared divided by the cube root of 3x plus 4 multiplied the whole thing by 1 over 2x plus 6x squared over x cubed plus 2 minus 1 over 3x plus 4. And yes, if you want to simplify this and it's driving you crazy, I'm sorry. It's just going to drive you crazy. I don't expect you to simplify it any further. So don't get all worked up over it. I know that's one of the biggest questions I feel that students have is like, how do I know when I'm done simplifying? Like, how do I know if it's simplified enough? Luckily, most of the points that are built into your exam are not, they don't have anything to do with simplifying, but there definitely are points that are in there for that. It is important to know how to simplify our answer because as a lot of you saw on the homework, especially for the chain rule, if your first derivative wasn't simplified, it made your second derivative much harder to take. All right. Oh, that was 3-4. I'm done with 3-4. You guys, I'm going to put up some homework. It might be tomorrow. And if you don't know what that means, tomorrow is at some point later on Friday, because it's technically like Friday early morning. I'm going to get it up at some point Friday. So if you're like really on the ball and you're watching this at like Friday 7 a.m., your homework might not be up yet. I'm sorry. I just want to make sure I check the assignment over before I actually put it in there. But who knows? Maybe I'll just do it and get it done with. Sometimes if I don't do it right away, I forget. Your test is on, I feel like I've written the same thing 1,000 times. Chapter 3 test, 3-1 through 3-4 is on Wednesday, 7/7. 6 p.m. normal class time, open notes, same as always. I'm proctoring you, same as always. And then you have no quiz on Thursday, 7/8, because we'd have nothing to quiz over, but we're going to start chapter 4 on Thursday, 7/8. Thursday, 7/8, no quiz. But we will have a quiz on that following Monday, the 12th. As usual. Your homework for 3-3, 3-4, remember, is actually going to be due Wednesday. So same date. Usually it would be due on a Monday, but we don't have class Monday. Might as well just have it due Wednesday. Give you guys extra time to work on it. Hopefully that doesn't mean you're waiting until Wednesday afternoon to do it, but you know, that would be your own problem at that point. There's nothing I can do about it. I'm going to see about having that office hour on Tuesday around 5 o'clock. I'll email you if I'm going to do that. It's very likely that I will, but I just need to double check first to make sure that everyone's going to be home and look at my calendar and make sure my husband is going to be available to watch the kids in case they wake up. Because it's very, very hard to have an office hour with 3 small children running around. That's all, though. Email me if you have questions or send them to me over WebAssign. If there's something I can't explain over WebAssign, then I'll just send you an email attachment. Have a wonderful holiday weekend, everyone, and stay safe. And I'll see you Wednesday.